So in this problem, we've got a hot sphere initially at a temperature of 500 degrees C, and it's immersed in an environment with a heat transfer coefficient of 30 watts per meter Kelvin and an ambient temperature of 20 degrees C. And we know the material properties of the sphere, its thermal conductivity, density, and heat capacity, along with its radius of 0.1 meters. The first thing we're going to do is calculate the BO number, which is equal to h times the radius divided by the thermal conductivity. We get a value, in this instance, of 4. And that should immediately suggest to you that lump capacitance is completely inappropriate for this problem, which is going to be, we'll find that the exterior of the sphere is going to cool down more rapidly than the interior. So what we're challenged with now is coming up with an expression to calculate the temperature at any value of R at any point in time. So to start with this, let's start with the heat diffusion equation in spherical coordinates. I'm going to eliminate some terms because of symmetry, spherical symmetry. The temperature is only a function of R and time, and our sphere is not generating or consuming any thermal energy. And we're also going to assume that the thermal conductivity is not a function of temperature, so we can pull it out of the first term. After simplifying the equation and introducing alpha, the thermal diffusivity, we're left with this partial differential equation. Let's take a moment to check the units. Alpha has dimensions of meters squared per second. 1 over r squared is 1 over meter squared. The partial also has dimensions, so 1 over meters for ddr, meters squared for r squared, and finally Kelvin per meter for dTdr. If we simplify these units, we'll find that the left-hand side has dimensions of Kelvin per second, and that's congruent with the dimensions of the right-hand side. To solve this equation, we're going to need one initial condition, and that's what we're going to say is that T is equal to some initial temperature, in our case 500 degrees C, at time equal to 0, and this is applicable for all R. The first boundary condition is a symmetry condition, and that says that the temperature gradient dTdr has to equal 0 at R equals 0, the center of the sphere, and this applies for all time. The second boundary condition applies at the surface of the sphere, and that's balancing the conductive flux, negative k dTdr, with the convective flux, which is h times the temperature at the surface minus T infinity. And this is applicable at R equals capital R for all time. The solution to this partial differential equation, subject to the initial condition and these two boundary conditions, is not particularly straightforward. You'll have to ask a mathematician how we got from there to this solution. The solution's tricky to implement for two reasons. One reason is this infinite sum, which isn't too hard, but the second problem is that this expression, these values of zeta, which is equal to the BO number, there's no way to solve for zeta analytically. The only way to get a value of zeta is to guess and check or use an iterative numerical solver. The way I went about solving different values for zeta was to first make a graph of y equals 1 minus x times the cotangent of x. And then what I can do is just read off values of zeta. Let's say, for example, that the BO number was equal to 100. And in that case, I can just find the intersection of 100, and I'll find that the value of zeta in that case is about 3.11. The second value of zeta is 6.22. The third value is 9.33, and so on. In our situation, the BO number is equal to 4, and I find the first 6 parameters, zeta 1 through 6, equal to the terms on the right. And I used those in my sum to come up with a temperature profile. In fact, I didn't use the first 6. I think I used maybe 150 or more. Probably overkill for this. So coming back to the analytical expression, once you've calculated a whole bunch of values of zeta, we can then import those into the summation. And now we're in a position, we know alpha, we know the radius of the sphere, we know the initial temperature, we know the ambient temperature. At this point, at any moment in time, we could solve for the temperature at any value of R. What I'm showing here is a simulation of that equation. The graph on the left is the temperature profile that we would see if lumped capacitance was reasonable. Of course, the BO number now is 4. It's completely unreasonable, but I'm putting it here just for reference. So we're going to start at an initial temperature of 500, and then it will asymptotically decay down to T infinity, which is equal to 20 degrees. On the right, I'm giving the true solution, the temperature again on the vertical axes. The temperature axes are the same. And then on the horizontal axis, I'm plotting radius from negative 0.1 to 0.1 meters. And once I start the simulation, take a look at what happens to the temperature profile as a function of R. What we see is a large reduction in temperature of the exterior of the sphere. It takes a while before the interior of the sphere even begins to change temperature. Another thing to take a look at is compare the temperature that we would predict from lumped capacitance to that of the true solution. The true solution, the temperature is much greater than what we would predict with lumped capacitance. And in fact, over a long period of time, lumped capacitance predicts a temperature that's below that of any location within the true solution. So now you're looking at an FEA simulation of the same problem, in which the BO number is equal to 4. Each frame in this simulation represents 1 minute, so it's occurring over 2 hours. We again see the rapid decrease in temperature of the exterior of the sphere and a slow decrease in temperature of the interior. Just to demonstrate something, I've now changed the BO number to 0.4. I've increased the thermal conductivity by a factor of 10. We begin to see a little bit better agreement between lumped capacitance and the true solution. And now I've increased the thermal conductivity even more, dropping the BO number to 0.04. When I run this, we find excellent agreement between lumped capacitance and the true solution. In fact, the true solution shows very little radial dependence of temperature at all. To further demonstrate the uniformity of the cooling, I've run another FEA analysis, this time with a BO number of 0.04 instead of 4. Each plot step in the simulation represents 10 seconds of elapsed time, and I've run the simulation for 30 minutes.